All right, so before we move on to more complicated type of gas, let me describe an interesting application of the classical distribution of the, say, the canonical distribution, the grand canonical, sorry, the canonical ensemble. So, so far what we have seen is that we have started with a microscopic statistical Hamiltonian, microscopic, partition function. And by moving the cranks, we have gotten some macroscopic, some classical thermodynamic quantity, right? But statistical mechanics is much more. You can use statistical mechanics to describe microscopic physics as well. And one of the more important application of this is known as the Maxwell-Boltzmann distribution. So what is this distribution? Often this is called Maxwell distribution, but it's also called Maxwell-Boltzmann distribution. And what it does is that it takes an ideal gas and it tells you what the distribution of the speed is. The speed of the molecules or the atoms, right? So this is interesting because you're using statistical mechanics to describe the distribution of microscopic quantities. You see, it's a qualitatively different kind of thing than what we've done before.
So many things can be explained through the Maxwell-Boltzmann distribution, right?
Exactly.
Speed.
Well, anything that is a function of the velocities. Okay, so what we do is that we just take the partition function, and the partition function, and what we do is that we just integrate over the spatial degrees of freedom. So we take a free particle and we integrate over the spatial degrees of freedom. And if our ideal gas has a finite volume, then integrating out the spatial degrees of freedom just gives me the volume of the gas, of the container that the gas is in, right? And what we have left is the integral over the momentum. So we are just looking at one gas molecule, but since we are thinking of them as non-interacting, generalizing it to n molecules is very easy. Okay, is this step clear, how the V came about? Because we are not...
We integrated dQp.
Right. Exactly. Okay, so let's go to the next line. So what we can do is that we are interested in finding out the speed distribution. And what we're going to do is that we're going to go to polar coordinates. In momentum space, but before we do that, we can, convert the integral into integral over the three components of the velocity. So we have an m cubed coming from that, and we're, p squared is m squared v squared, right? So of course, this just depends on the magnitude of the speed. And therefore, we can do the angular integration in polar coordinates, and that's just going to give me a factor of 4 pi. And then what I'll have left is an integral from 0 to infinity dv, where v is the speed, the positive speed is a positive quantity, times v squared. And then we have, this comes from the measure, right? And we have e minus e to the power minus beta m v squared by 2. Okay, is everything clear with this step?
Sir, by measure, do you mean units?
No, I mean, when we do, if you have, say, dx, dy, dz, and you go to polar coordinates, what do you get? You get rho squared, and then you get sine theta, d phi, d rho, right? And then these are the, and you have some function which is a function of just rho, function of rho, that is the integral. So because the integral is just a function of the rho, you can do these other integrals, and that's just going to give you a factor of 4 pi. And what you have left is rho squared d rho, and then your integrand f of rho. So here, so where is this rho squared coming from? It's coming from this measure, this integration measure, right?
Oh, I see. The
From the
differential
Jacobian.
volume element.
Yeah, the Jacobian, yeah. So, yeah. So this is v squared coming from the Jacobian, okay? All right, so now what we can do is that we can now do the, well, what is,
Sir,
yeah.
how does a 0 to infinity limit come from the previous line?
Well, yeah, the 0 to infinity limit, if you look at this thing, this has a geometric interpretation where rho is the polar vector, right? So it's a distance from the origin to the end. So is this a positive number or not?
It's a positive number.
Yeah, so the integral here would be from 0 to infinity, right?
We're just taking the whole space,
Yeah.
the volume.
Yeah, no, because the thing is that the momentum can be anything, right? Momentum, the volume is finite, but the momentum can be anything.
Also, this is the momentum space.
Yeah, because that's what I've done is that I've taken p and I've expressed p in terms of speed. P squared in terms of speed squared, right?
Okay.
So and the speed squared then goes from 0 to infinity, right? Because the momentum also went from the magnitude of the momentum also went from 0 to infinity, right? Do you want me to do this more carefully? I can do this. Just let me.
No, I understood.
Okay, good. All right, so so now if I look at this expression, what is this? This guy is some sort of probability distribution, right? So what we should so the probability distribution, so if I look at this on the right hand side and think of it as a probability distribution, then the probability that we have a particle at speed v in an interval dv around v should be given by some normalization factor times v squared e to the power minus beta m v squared by 2 dv, right? That's what, what is the meaning of the partition function, right? The meaning of the partition function is that it gives us the probability that that particle has a particle of this energy, that the particle of this energy is in that state, right? That's what this thing is. So, and we have some factors which we can treat as normalization factors. So therefore, and the partition function is the sum over all these probabilities. So the probability density function should be some normalization times the stuff that depends on V. Right? Does that make sense? It just comes from the fact that we can think of the partition function as right? What was the partition function? It is the sum of all the probabilities, right? Does that make sense? Remember the partition function was there to give normalization. So, the Boltzmann distribution was something like e to the power minus beta h of n, right? Or e of n. Remember that? And then we said that is to actually get the probability, what we have to do is that we have to divide by all the sum of all the probabilities, right? Because we need this thing to be normalized. And this thing is what we identified as the partition function. So, which means that the partition function has the interpretation, it is the sum of all the unnormalized probabilities, right? And that's exactly, so if I do that, what I'm saying is that we have all these different states. Each of this state is given by different speed, and we are summing over all these states. Therefore, the probability density should be given by something like this expression up to the normalization, because we want to normalize this thing without the integral. Okay, does this make sense? This and this. This is an important point. I don't want to gloss over this.
So we're basically normalizing the fact that it's unnormalized.
Yes, I mean the partition function is unnormalized, right? But the fact is that the partition function has the interpretation that it's the sum of all the unnormalized probabilities. So here we have a sum, we have an integral over here, right? The integral over V. So what we're saying is that these guys, that this factor has the interpretation of a probability density.
Okay.
Okay. All right. So yeah, you should chew on that. So, and because, so we are defining this to be the probability distribution over the speed. This is the Maxwell-Boltzmann distribution. We haven't solved it yet, but this is the Maxwell-Boltzmann distribution.
Is that supposed to be the result of this integral?
No, we haven't done the integral yet.
So how does this equation relate to the integral? I'm not exactly understanding that.
The integral is supposed to be a probability distribution, I guess.
Yeah, the integral is just the sum of over the probability, unnormalized probability density, right?
So we're comparing it with the equation FB dV.
Right. The thing is that, I have not specified what n is. N will be determined by the fact that when we integrate this, we were going to demand that the integral gives me 1, which is not something that I can demand here.
I see. So is
Okay.
this kind of like what we're expecting to get something of this form?
Well, just hang on 1 second. Okay, so the next thing that we are going to do is that we are going to find out what n is, right? So we demand that our Maxwell-Boltzmann distribution gives us 1 when we integrate over all the speeds. Okay, so, and if you do this, then, you know, a couple of lines of algebra, and all you need is, well, you need to do something that is kind of a Gaussian integral. And let me just show you, because some of you may be unfamiliar with this. So the integral that we're doing is from 0 to infinity of v squared e to the power minus b beta m v squared by 2 d of v, right? And then, you know, we know how to do Gaussian integrals, but this is not exactly a Gaussian integral because there's a v squared here. So what we do is that what we just say, okay, n, let me just, if I take a Gaussian integral from 0 to infinity of e to the power minus beta m v squared by 2, and I take the derivative with respect to beta, then I'm going to bring down a factor of minus m v squared by 2, right? And I'm going to keep the v squared here so that I can do this integral, but I'm bringing now this factor of minus m by 2, so I have to multiply by the inverse of this. So I multiply by minus 2 by m, okay? But this is an integral we know how to do. That's just a Gaussian integral. So we have minus 2n by m d by d beta, and this thing is just going to be 2 pi by beta m. But here you see that the integral here is from 0 to infinity, not from minus infinity to 0 to infinity. So there should be a factor of half dividing this. So there should be a factor of half. So I'm writing that, okay? And yeah. So when I do this, and I take the derivative with respect to beta, then we get the result that n over 4 pi. I'm just writing the final result. You should work this out. I'm writing the final result in a nice form, that is. And we want this to be equal to 1. That means that n has to be 4 pi m divided by 2 pi kbt to the power 3/2, okay? So with this value of n in this equation, let me just box this equation. We get the Maxwell-Boltzmann distribution, okay? So let me just draw some pictures of the Maxwell-Boltzmann distribution. So here on the x-axis, we have the speed. And on the y-axis, we have the probability density. And for, of course, this is going to be a function of temperature. So we have something like this, okay? So, and so as the speed goes up, it becomes a Gaussian, but for small speed, it goes to 0. Okay? Any questions?
Sorry, you took out the v square and neutralized that with 2 by m or something. So how did you take the v square out if the integral depends on?
No, I didn't. I didn't take out the v squared here. See, if I this is beta. This integral should have a dv here. This is beta. This is a derivative with respect to beta, so it can go inside the integral, right? because the integral itself is a function of beta, right?
Yes, sir.
So if I take this inside, even after you do the integral, it's still a function of beta. So because this integral converges, I can do these operations. So if I take the derivative inside the integral, then this guy acting on the exponential brings down a factor of v squared, and then this guy is gone. So from here we go here.
Oh, understood.
And this extra factors of m and half is taken care of here, and the minus sign as well. Okay. So this is a trick for, basically given this result, you can find all the moments you can find all these moments, right? And for odd n, this is 0. But basically, the way to find out all the even integrals for even n is to just take this and take the derivative with respect to x. Sorry, with a. Sorry. Okay. There's a trick.
Yeah, got it.
Okay. So now, according to the Maxwell-Boltzmann distribution, what is the average velocity squared, the speed squared? The average speed squared is nothing but n, 0 to infinity, v squared, f of v, d of v. And I leave that as an exercise to do this, and you can show that. So now the integral will have v to the power 4th. If you do this, you get 3 kBt over m, and therefore the average energy of your gas will be half of gas molecules, half mv squared, which is 3/2 of kBt, which is exactly the result that we derived before. Remember that when we did the equipartition theorem, the equipartition theorem gave us exactly this result, right? So things are very consistent.